Hello, everyone. So first of all, how was the conference? Give it to the organizers, guys. Give it to them. I have to start by saying I'm sorry. This talk is not a palate cleanser. It's going to be a technical talk with a lot of assembly, C++, and bad things that people can do in C++. So this robot is a representation, or Android is a representation of what I feel when I go into code bases and I see Reinterpret. It's a horror. Usually it's a horror show because people don't understand how it works. They're just slapping it everywhere because it works. It's a magical thing. And the most horrible thing about this Android is it's full of rust. I don't know if you see it, but it's full of rust. Horrible. And if you're using it, you're probably misusing it. This talk is not going to be a talk about how bad C++ is. This is not my point. The point of this talk is to show you the problems and how to use the tools correctly. I will give you the tools to use Reinterpret correctly, and I will give you the guidelines that you should keep using if you really need to use Reinterpret where you're using it. A little bit of shameless self-presentation and promotion, of course. So Mike did a wonderful job. I don't need to say anything about myself, except a couple of things. I have a LinkedIn where I post about C++ a lot. And please, if you like C++ and you like Riddles and you like things and learn new stuff about C++, you can follow me there. I have a forum where I basically write more things and I explain and dig more into details about the things that I write in LinkedIn. And for the last year, I'm maintaining a YouTube channel that's called CppNext, where I'm really digging into stuff. Each episode is around 10 minutes. And I have to tell you, doing YouTube is the hardest thing of all. It's really hard to maintain it. It's really hard to understand why people are watching the first 40 seconds, then dropping to 0, then going up again, and then dropping and going up again. But I really try to do it each month. Each month I have an episode, and it's going on for a year. Hopefully I will keep doing that, because I enjoy it a lot. Who liked Scott's talk today? I enjoyed Scott's keynote a lot. And because I heard it, I know that I have 331 million keystrokes left before I die. But at least I know that those keystrokes are going to good, for something good. I'm trying to teach. I'm always trying to teach. I'm not a gatekeeper for knowledge. So that's why I do the forums. That's why I do the LinkedIns. That's why I do the YouTube channels. I want you guys and everyone, guys, girls, everyone to understand how this wonderful language works, to understand how we should work with it, and just push it forward. This is not the monster that people say it is. So hopefully you would enjoy it. Not everything in this talk is going to be about technical stuff. I want to tell you a story, storytelling. So everything started about 5 months ago when I got a very cryptic mail from Chris Ryan. If you don't know Chris Ryan, he's a wonderful speaker liaison of this conference and many other conferences, and he's a good friend. He's trying to be. So he sent an email, and I'm quoting, "Expect an email for Amond." What should I do with it? I don't know what to do with this. So I waited for a week, and then I sent him an email back and said, Chris, Amond is not telling me anything. Maybe you can tell me something? No, it's above my pay grade. That's it. So I waited for another week, and Amond actually contacted me and said, okay, we want you to come and give a keynote. And I was really excited, because this is not my first keynote, but this is my first keynote before a live audience. I did it in Zoom and on other stuff, but live audience is always much, much better. So be nice or throw tomatoes. I don't care, I'm here. Another thing is that I remember that CppNorth likes keynotes to be not technical. That's how it works here, a little bit. So I got a little bit anxious, and I spoke with a friend, Pierre. Hello, Pierre. And he's part of the program committee right now. And I told him, what do you expect from me to do? So, Pierre, we will talk about what you gave me, the answers you gave me, in a little bit. But I want to start with a very important thing about Pierre. Pierre is a bad photographer. I don't know if he's a bad photographer for everyone, but he butchers me. So let's start with an image from the previous conference. And this is his best work. He caught me here. So I don't know what he tried to do here. He just wanted to show me how sad I am when I'm sitting. Yeah, he wanted to talk to me. But here it is. That's not the best work. That's the best work. Then we have this. I don't know what it is. It's me walking, and it's blurry. I think it's artistic. That's what he tried to do here, something artistic. Toronto in the background. Yeah, wonderful. And now we're getting to the crown, the jewel in the crown. Here it is. This is the best one. I love it so much. He actually published it 3 years ago on LinkedIn, and everybody saw it, and I was so excited. Hey, yeah, I am so happy. Yes, this is my best picture yet. Pierre, please stand up and bow. The artist, everyone, the artist. Except, let's forget that. He is an artist. But what Pierre told me made me a little bit anxious. So he's telling me, we are putting you as probably a technical keynote. Compared to Kate, you know. It will be probably, but you can surprise us. You can surprise us. So I was like, probably technical, lol. I was not laughing. Yeah, I'm a technical nerd. I am a technical nerd. I think it's my best feature to be technical nerd. So I want to be a technical nerd. But then, Pierre told me something else. If you're going to do something technical, don't do it about AI. And now I have to speak about AI. So I will make it short. In my opinion, AI tools are great. You just have to remember one thing. They are tools in your control. They are helpers. They're stupid, and you are the smart one. You need to know how to prompt. You need to question it. You need to ask you questions again and again, and you have to know your tools as well. So in this stage, where AI is taking your jobs, it's not. It's horrible, especially with C++. So there are different AIs. There are AIs that are better with C++, like Anthropic Claude. It's not bad, it's getting there, but it's still bad. You still will need to write the code. You still will need to understand the language, because the hallucinations are amazing. Sometimes it outputs things that you just cannot understand. Where did he get it from? It's not even written like that. He just suggests something that it's not there. So it's your job to be the creative one and to write code. I use a lot of AI. During this presentation, I used the AI for spell checking. I used the AI to tell me, is the flow okay? It's good at those things, but not more than that. Because I got anxious, I said, I cannot decide. I want to be prepared for CppNorth, and I want to do something good for here. So I decided I will create a survey on LinkedIn, and I will give 2 options. One option was the Reinterpret one that we are doing today, and the other one was CPP Never Sleeps. Do you know why I wanted to call it CPP Never Sleeps? Someone can think about it? It's a song from Neil Young, Rust Never Sleeps. So CPP Never Sleeps is better, in my opinion. I even started creating the graphics for the talk. So here we have me in Devil May Cry outfit, and a crab behind us, the evil, evil crab that is trying to take our jobs. And someone told me that the crab looks too scary, so I made him a little bit nicer, but he's still an enemy. But in the end of the talk, we will be friends, Because we don't have to be enemies. Each language has its own good things and bad things, and we should work together like frenemies. We will be frenemies in the end, I hope. Because Rust is a good language. And what did you do? Nothing. Undecided. 2 weeks, 216 people. And it was 108 to 108 exactly. Moreover, after this, my good friend Amir Kirsch decided to send me in WhatsApp and told me, hey, if you're going to do a talk about Reinterpret, it's going to be hard to deliver because Reinterpret is very niche, but if someone can do it, it's you. Thank you, Amir. Undecided. So I had to take action, and I decided. CppNorth, it's you and me. 20 minutes adventure, what could happen? Classic Alex. Just a little bit assembly, compilers, and you be in the closing keynote for CppNorth. That's a first. So let's go to the adventure and let's start misusing Reinterpret. Sorry, I meant let's start using Reinterpret correctly. This niche little thing made me write 105 slides just about Reinterpret. And just about technical things that we need to think about. So how simple and niche is this thing if I have so many things to say about it? And this is, people think it's niche just because they're using it as something very simple, but it's not. And let's go into it and try to understand how to use it correctly and how to make our programs safer and better. So let's start with a definition. I've created a table with all the casts that we have in C++. We have the favorite one, static cast. It's static, it does everything in compile time, it checks for you, it's safe, everything is good. We have dynamic cast, which is not bad, might have overheads, people say. But the problem with dynamic cast is that we must have RTTI. Const cast, Andre talked about it, and Amir talked about it a lot. It's a horrible, horrible story, but this is for another talk. We get to talk about the worst one, Reinterpret. It's dangerous, it does nothing, it's hacky, it's fun. So, in simple words, Reinterpret translates between types. Unlike static cast, usually it doesn't create any instructions. It does nothing. It's basically telling the compiler, hey, you think you have a type there, it's a different type. So think about it as you have an object of an elephant, but you're Reinterpretting it into a frog, and in the memory it's something like that. Moreover, if you go to CPP reference and look at all the rules that you need to know about Reinterpret, it's horrible. It's a never-ending list of things that you have to know before you're using this simple cast. If you really want to read everything and know everything by heart, here's the QR code for that. But I'm here to help. In simple words, again, in simple words, for Reinterpret to be safe and to do what you think it's doing, type must be layout compatible. That means type cannot break strict aliasing. We will talk about it in a bit. And converted type need to be the same as. Sounds simple. After this, we will start all the C++ and breaking stuff and understanding how stuff are break. So don't panic. Everything will be okay. Let's start with something simple. We have 4 classes. A has an integer inside it. B has an integer and a function. C is inheriting from A, and D is inheriting from both A and from B. If we will write something like that, is it valid? Hands up. It is valid. So people that put their hands up, it is valid. Because we are doing nothing. We're basically saying, okay, this is an elephant that should be a frog. But we are not doing anything bad. Yeah. We are not doing anything bad here. But if we will do that, is that okay? And practically? But it is an undefined behavior. So basically, because the types are not same as, they don't have inheritance from each other, we cannot say that A is B. So we cannot re-entropy cast one to another. We can do the cast itself, but when we are actually accessing the memory, it's considered to be undefined behavior. So a simple thing like that, nothing will find it. It's basically something that is fine from the language, but it's undefined. Now let's go to C. If we will create C and re-entropy cast C into A and use A, is that okay right now? Hands? Yes, that's okay, because right now C is A. C inherited from A. That means that C is exactly like A, and we can do it. We can actually access the memory, and we can use it safely. Basically, one of the safe things that you can do with re-entropy cast is upcasting. When you know the types and you know that you want an upcast, using re-entropy cast is perfectly fine, because it's exactly what it can do. If something is the same as something else, there is no problem with it, and we can use it. But let's talk about another cast here. Let's talk about re-entropy cast vs dynamic cast. We said that dynamic cast needs RTTI. In this case, we have RTTI, so it's fine. So what I try to say here is, let's look what will be better for our usage. We have A, and we are translating C to be A again. We said that it's fine. And if we would look at the assembly code for it, we can see it's just a move, nothing more. If we will do dynamic cast, will it produce more assembly code? Who thinks yes? Maybe it's not an answer. Yes, more. So more people are saying that no, and they're absolutely right. Dynamic cast did not produce more code here. It produces the same amount of code. It's the same move to initiate A2. Yes. Mm-hmm. And if we would look at micro benchmarking for this, of course they both run the same, because they're nothing else. It's just moving things around, and that's it. So in this case, even in this case, I would prefer to use dynamic cast, and I will show you why. Let's say here we are using, again, we are re-entropy casting to C to A. Oh, sorry, my bad. You might say that this is something that will work only for x86. So I will show you that it works on different architectures as well. So here we are doing the same code, and I'm using my favorite CPU, RISC-V 32 bits. So in RISC-V 32 bits, we're creating two assembly lines, load and store, that's it. For dynamic cast, again, we are just creating load and store 2 bits, and that's it. That means we can use dynamic cast because dynamic cast is much, much safer. Now let's look why is it safer. Now we're creating B, a pointer to B, and we are re-entropy casting it to A. We said that this is fine. Nothing is broken here, nothing is bad. But already, if you will use dynamic cast, you will get an error from your compiler that will say B is not polymorphic. Why not to use that? If nothing bad will happen, you will not get overhead from the code, but you will get more safety. Why not use dynamic cast in these cases? Furthermore, let's look at C. We are creating a new C now, and we are re-entropy casting it to A. C is fine, right? But you have to notice one thing. In line 11, I did something different. I put a void there, void pointer. So if we are using void pointer in this case, dynamic cast will alarm us. It will say, hey, you're using void pointer. Void pointer is not a class type. You cannot do a re-entropy cast or a dynamic cast to this. So you need to think about it. And again, the compiler is helping you just because you're using something different than re-entropy cast. without a cost. And if we will use GCC, it's even better. It's saying cannot dynamic cast be to void class. Better error messages, in my opinion. It was reversed. So why are we even talking about void pointer? Chris, why are you talking about void pointer that much? Just loving something bad doesn't mean it's something that we should use, right? I love Coke, like Coca-Cola, but it's bad for me. So we should stop drinking it. So here is another example. Prefer using C++. We are C++ developers. We have something very specific that does exactly what you want, as if it's a void pointer here. So we have any. We can create an any type here, and we can any cast it to C pointer, and then dynamic cast it to A pointer. And this is fine and safe. This is ugly as hell, but you need to understand that if you're doing something like that, it's supposed to be ugly. You need to look at it and say, am I doing good software engineering if I do something like that? Maybe you have to do it, and that's fine, but maybe you're not. This is just a reminder to show you that D is inheriting from A and from B. So right now we're creating a new D, and we are re-entry casting D into B. Is it fine? It will compile. It will compile. But if we will just listen to our compiler, we will not do that. So here, even with re-entry cast, it's telling you, hey, you're doing something wrong. Please don't. I'm not what you think I am. So you should always listen to your compiler. And warning should be errors. This thing should be an error. You should not use a program that actually compiled something like that, in my opinion. Now let's go to something really interesting. Strict aliasing. Look at this Android. They are very strict with each other. So what is strict aliasing in C++? Who knows? Okay. Strict aliasing in C++ means that two objects of different types cannot have the same address in the memory. That means an integer and a float, for example, cannot have the same location inside the memory. But it's so easy to break it with re-entry cast. So easy. Let's look at this simple function. You have a function that receives int pointer and float pointer and returns an integer. It sets I to be 1, and it sets f to be 0.1 float, and it returns the reference of I. In this case, the compiler, because of strict aliasing rule, may say, hey, I know what you're returning here. You want I to be 1, you're returning I can throw everything away, I can set it there, but I don't need to do reference again. I will help you. I'm a friend. I will do it faster. So, with that in mind, now we're doing this in main. We're creating an integer, and we're returning a function, foo, with a pointer to an integer, and re-entry casting it the same pointer to a float. What will return? What will be returned here? Yes, depends on optimization. But why? Because it's UB. You broke something that shouldn't be broken. But yes, it depends on optimization. If you put optimization of O0 here, it will return what you expect. But who works with O0? In any case, you have to understand that it's so easy to break it with re-entry cast. So easy. It costs us nothing to break a very important rule in C++. And if you would look at the assembler code for that, we will see the function itself. It's setting 1 into the pointer. It's setting 0.1f into the pointer. Then it just says, I know what you want to return. So into the return register, we will set 1, and we're returning it. And if we would look at the main, because the function was easy enough to inline, and there's so much dead code in it, And all it needs to do is return 1, so all it does is returns 1. That's it. So not even setting the memory in this case. Speaking of even floats, this can be really explosive. So let's look at this integer. It's a 10. And let's say that I saw it hundreds of times in many different code bases, that people are just doing this. They are taking a pointer to an int, re-entry-casting it into a float, and setting it to a float. Happens a lot. This is undefined behavior. Floats and ints have no relations with each other. So doing something like that, this is undefined behavior. If you are doing it, most of the compilers will do it fine, but you have to know that this is something wrong. How you should do it, it's not even perfect here, but there is a type that re-entry-cast can always cast to and cast from. Byte arrays. We can cast any type we want into a byte array, and we can cast back from it to any type we want. So here, if we will take the integer and cast it into a byte array, and then cast the byte array into a float, that should be fine. That removes some of the problems that might happen. But there's another problem. Here, the problem is that I changed the float to be double. Double has 64 bits. Int has 32 bits. So I'm basically trying to do something to look at the memory and extend 32 more bits here. And if we would look at the result of the print, we get 10 and a very, very, very small number. Why is that? Why? Why life is so hard? So let's try to be naive and say, maybe there's undefined behavior here. And the undefined behavior is basically because we try to extend the integer. So if we look at the integer itself, it's represented by 000A. But if we will extend it, maybe there will be some garbage in the 4 bytes that we didn't want to take. And we are mandatorying it. We are now taking 8 bytes instead of 4 that were actually initialized. And Tony talked about it this week. Initialized data is undefined. Uninitialized data is undefined behavior here. So this is a problem. But again, it depends on optimization. So with optimization of O2 and higher, you get zeros on Clang and GCC, on Linux. So this is not the problem. The problem is because double have a different representation than int, and this is the actual representation of 10.0 in double, it's 4024, you get a different number. And people are really, really forgetting that. They think if they put something into a float or a double, they will get 10.0. It's not that. It's not that. Even ints can misbehave. So it's not just doubles and floats. Let's look at this integer. We have an integer. Instead of killing the beef for once, I'm feeding the beef. So we are feeding the beef, and we are re-entry-casting it into 64-bit integer. It was 32, now it's 64. We want to print the data here, and voila, we are just taking uninitialized data for integers as well. This is bad. Even though that integers are integers, we are doing something that is really, really bad here, and that this is pure undefined behavior. But again, if I do it with O1, it's fine. The previous one was with O0. This one is compiled with O1, and everything is fine. That is what's so wonderful about UB. It might work all the time, and then it doesn't. Now let's do it in reverse. So this is not a bug per se, because sometimes you really need to do that. But what happens here is we are creating a large number with 8 bytes in it, and then we are re-entry-casting it to be a smaller one, and people tend to forget that as well. You are truncating the number. So I've seen this, really, all these little things that I'm showing you here, I've seen it in our code bases. I've seen people trying to do re-entry-cast to those types, and they don't understanding why the hell they need to debug it for so long to understand that they're taking a larger number when they only had 32 bits? Or why the hell my number doesn't have my sign point because I just truncated it? But it happens. It happens a lot. Yeah?
Does the result depend on endiness here or no?
Yes, of course. Because if the endians will be the other way around, it will take the other 4 bytes. What we really want to do here is bitcast. So bitcast is something that was added to the language in C++20. It's very safe because it's copying all the data around, and it's turning the numbers in a correct order and in a correct way, and we always will want to use bitcast. So if you have an urge and an itch to do Reinterpret, think about doing a bitcast. But there's still a catch about bitcast. Bitcast does not work on types of different sizes. Here we are trying to do the cast from int to double, and it is telling us, hey, you cannot do this. So to do that, you need to jump more hoops, and we will get to that soon. To make things even more interesting, and this is one of my favorite things, Booleans. It's such a basic little thing in the language, but this basic little thing in the language does a lot of wonderful magic when you have your B. So let's start with this application, and we will start with Clang. We will go to GCC really soon. So we have an integer that's initiated to F6. Then we are reinterpretting it into a Boolean, and then we will just want to print what we will get here. So what do you think the Boolean will be in this case? True or false? Who thinks it's going to be true? Who thinks it's going to be false? Hands? And nobody knows. It's false. Let's look at the binary here. The binary is important. Let's go to the other slide. So let's make a little small change here. And we will change F6 to F5. And we are basically doing the same thing. What will be the result here? True or false? That's right. That's true. And why is that? No, because Clang decided in its implementation to look only on the last bit. They decided to do that. They can do whatever they want. It's undefined behavior. So they decided to do it like that. Now, let's look at GCC. Hey, it seems that the GCC is doing the right thing, right? It's true and true. Wrong. Let's look at this. So we have 32 bits that everything is ones, but the last byte is zeros. What will GCC do? False. So in GCC, instead of looking at the last bit, they decided to look at the last byte. Fun. And that's undefined behavior. You can never rely on those things. They will work differently. Tomorrow, someone in a GCC implementation would say, hey, I want to do something else. Let's look at the middle byte. It will be fine. Unaligned memory access. Who knows what unaligned memory access is? Almost all the room. Amazing. So unaligned memory address is really important to understand. Unaligned memory address is when you're reading bytes from a memory and you want to read n bytes from it, but you are reading from an address that is not aligned to that size. Basically, if you take the address and modulo it by n bytes that you want to read, it is not equal to 0. So what's the big deal you're saying? It's performance. On x86 and on ARM, it's performance cost. There are some processors that will even throw a processor exception. And that means your program will be terminated. And again, it's so easy to break it with Reinterpret. So we have a char array here with ABCD. And when we are doing this, this is fine. We are just reading 1 byte from the array. The array is aligned to 8 bytes. Reading this byte is fine. But in line 66, when we are trying to Reinterpret from the index 1 and to make it uint16, This is not fine at all. This is unaligned memory access. The memory is aligned to 8 bytes, but you want to read 16 bytes from an address that is not divided by 16, and you get performance cost here. As I said, x86 does the job right. It just does what you want it to do. And the worst part is, it's not even warning you. It's not telling anything. You are using unaligned memory address, reading from it, accessing it, shooting yourself in the foot because your performance gets worse, but the compiler says nothing. It's all good. So here, why sanitizers are your friends. Again, Amir did a wonderful talk and he explained about other sanitizers. In our case, undefined sanitizer is the important part. So only if you run UB sanitizer here, you will get this message. And this is a very self-explanatory message. It says, hey, you're trying to read UIN16 from something that is aligned to 8 bytes, and here's the nibble that you are trying to touch, and it's not aligned. So fix that. Please use sanitizers in your CI. It will save you so much grief later. What you should actually do here is mem copying. Mem copying from the byte array to an actual UIN16, it's perfectly fine. It's perfectly safe. You are reading the byte by byte, and it's perfectly aligned, and you will get the correct answer. But you may say, mem copy is expensive. What about performance? What do you think? What will run faster, unaligned memory access or mem copy? Someone thinks that unaligned memory address will run faster? No. And it's 10% slower. Not by a lot on x86, but still 10% slower is 10% slower. So you need to take care of that and to see that you are always using aligned addresses. Unaligned RC is blue, and aligned MC is yellow. Now let's talk about the magical part. I mentioned this magical part of creating cars from flowers, or in Reinterpret, it's creating anything you want from bytes. So you can create anything you want from those bytes. And let's look at this little code snippet. This is a very small thing, but I wonder who will recognize the pattern here. So we have a struct with an int inside it. We are creating a char buffer or a byte buffer here in the size of x. It can be larger, size of x multiplied by something, and it's aligned to x because we want everything to be aligned to x here. Then we are in placement new an x into that buffer, and then we are reinterpretting it to x from the buffer and using y. Is this fine? First of all, what pattern is this? Anyone recognizes? This is memory pool. You can create a huge memory pool and can use different objects inside it. In this case, it's just aligned for x. So we always will create multiple x's inside this memory pool, but we will take memory chunks and give it back to the pool. And this is a very, very simplistic one. So now let's go back to the main question. Is this defined behavior? Who thinks no? Is this defined behavior? This is undefined behavior. This is undefined behavior because the problem is here, and the problem here is tricky. We have created bytes. We are reinterpretting the bytes to x. But the compiler may try to optimize it out because it's not really understanding that there are actual x behind those bytes. So doing the reinterpret is risky. And some compilers in some types may do a mistake here, and that's why it's undefined behavior. So the way that you should go here, it's what with this little function that was created for C++ 17 that's called Launder. Launder is basically laundering the memory. It says, hey, compiler, don't worry. I will wash the memory for you, and it will become X. So in this case, this is totally, purely defined behavior. It's a small change, and you really need to start using this function. It's really nice. It almost does nothing. We will talk about it right now. So it's just laundering your memory. This is the function. That's it. It does nothing. The function is basically getting a pointer in from type T and returning a pointer of type T. But because this function is returning a pointer and receiving a pointer, it has side effects. And because it has side effects, the compiler may not optimize it out. And that means that it always knows that the return type here and the type that they are trying to use is an actual T-type. And that makes your program safe. So if you really need to do something like that, use Launder. But even with Launder, things can get explosive. Launder is not enough. You have other patterns and other things that you need to think about that may explode your code. So let's talk about them. This is an example. We have a struct X with X and Y in it, and those are arrays. And I bet this is something that you see a lot here, and you're doing it yourself many, many times. If you're working with network, you're always receiving a chunk of bytes from network, right? And you need to process those bytes, and you will usually process it with Reinterpret because that's how we learn to do that. So here we are doing this thing, and we are Reinterpret it from buffer to X, and we are laundering it, and then we are using it. Is this fine? Is this defined behavior? Anyone? Defined behavior? Hands? This is undefined behavior. And this is undefined behavior because we are not thinking about lifetime. The object that we received from the network is not there. It's not, no one started its lifetime. No one actually created it. We are just Reinterpret something that is not there, and it's considered to be undefined behavior. When an actual object lifetime starts, you can see in the disassembly of that program, you can actually see start lifetime here. That's on Clang. I'm not sure about GCC. On Clang, you can actually see start lifetime and lifetime, start lifetime and lifetime. So without it, that's pure undefined behavior. What we should do here is to do it like that. This pattern may seem weird. So we are creating the X struct that we want to use. We are mem-copying the buffer that we received from the network to D. We are using it as expected, and then we are copying back. And if we will look at the function disassembly, we will see that it creates the same code. And that's because the compilers are smart enough to see this pattern, and they are smart enough to understand that, hey, you're mem-copying something, using it, doing something on it, and then copying it back. Probably you just want to use the memory itself. So it removes everything out, and it optimizes it to be the same. So the mem-copy part here is not expensive, and you will not pay for an overhead here. Everything will be fine. But the problem is that compilers may miss. And you may have a very special case where you are reading it and then you are writing it in another location and the different compile objects, and it's something that will get lost and the compiler won't be able to see it. And then that's a problem because you will have overhead. And we are C++ engineers, we love things that run fast. We love speed. So in this case, what you actually need to do is to use C++20. Because in C++20, mem-move, mem-copy, and new are starting lifetimes now. So that means if you are mem-moving something, you are starting its lifetime. And here in this example, what we are doing is we're basically moving the buffer to buffer. And because we're using mem-move, it does nothing, just starts lifetime. So you're not paying for the mem copy. You're not actually copying. You're not actually moving. You're just adding, hey, the lifetime of this object has started now. So everything is okay. Don't worry about it. It's totally defined behavior. And that's how it should be used. And if we will look at the disassembly is the same for this as well. So we just have to move operations, and that's it. Now in C++23, things will get even better because we get specific lifetime operations. We can say that we got something from the network, and we're just saying start lifetime as X, and giving it a buffer and using it, and everything is fine, and C++23 should be already totally implemented, but it's not implemented anywhere. So use the mem move. If you actually have access to C++20, this is the way to go. Use mem move, and it will be fine. The moral of the story is that we are not done yet. We have more to go, but I want to summarize something a little bit here for you to get from this part of the talk. So with great tools, and Reinterpret is a great tool, a very scary tool, that you need to understand how it works. You need to understand the tools in C++ and in other languages, but especially in something that has so much power like Reinterpret, we need to understand what it does and what it doesn't do. We need to understand all the pitfalls. I covered many of those, but there are many yet. You can still find other things. How do you do that? You need to understand, you need to read, you need to try to write code to understand how it works. What I'm doing is basically going to code bases where I work, and I solve bugs for people, and then I go and I talk about it. But you can just go to Compiler Explorer and write Reinterpret to anything and find out. And it's horrible. And the most important thing here, if you can, use a library. If you're writing the library, hide all those scary things away from your user. Do everything yourself, because you're the one that's writing the library. You know what it's supposed to do. You know how things should work. The user most certainly not always will know what to do, and most users will do something bad, like the thing that I showed with the strict aliasing breaking. That happens. Sanitizers. Sanitizers are your friends. Always, always, always run sanitizer. It costs nothing to run a sanitizer during CI. You already have CI/CD. Why not run debuggers, sanitizers, and everything in it and fix all the bugs? And the most important part here is UB is bad. People are using UB for advantages. I saw that with integers. I had a talk here last year about toInt or toUint, and people actually used int because it had undefined behavior and it made the program much faster, and they were very happy. But then it broke. So don't trust UB. If you have UB in your code, this code is bad. And as I said, I'm here to help. So I mentioned that you should hide everything in libraries, and if you can, you should use a library to do something for you because someone worked on it and tried to go over all the edges and make the sharp edges a little bit more dull. So I worked on the library for safe casting. I really was annoyed by people doing the same mistakes that I showed you here. I decided to write a library that does the work for them. And this is actually something that is used in speed data, but is fully open sourced, and you can use it. This is the QR code if you really want to play with it and to look at it. And we will just go a little bit behind the curtain soon. But let's start again with a small example. Let's say that we have a simulator that we need to write. A simulator for a hardware. Let's say it's a hardware that knows to work with floats and ints. But when it gets to the computation center in the hardware itself, it always has to be uint64 because the hardware doesn't know how to work with floating points. that means to work, to actually calculate those things, they need to be represented as uint64, and then get back to the actual type that they need to work on. This is an actual hardware that I have, and this is a simulator that we had to implement. So if we would look at this function again, we basically do all the hoops and all the jumps that we're supposed to do to make things work. We're using lambda, we're casting to bytes, and then to uint64, and then dereferencing it, but it's still problematic. I already showed you a taste of this problem, but to make it a little bit clearer, let's make this function not to uint64, but a generic function that can cast to anything, any uint type. So here it's basically the same function, just we are returning it 2, and we are casting to 2 instead of uint64. And in the main section, we have a float. This float is 256.2. We're printing it, and then we're casting it to uint32, and then we're we're casting it to uint64 and then printing it again, and we get different values, totally different values. So if we will go snooping around a little bit and we will say, okay, I want to see the bytes, I want to see the hexadecimal code here, and I want to understand what's going on, we can basically see that the bytes are there. What we want is there, but we already mentioned that we have this problem. And with Lambda, by the way, it doesn't care. It still has the same problem with optimization, without optimization on Clang. I'm not sure about GCC, but on Clang, it acts exactly the same. So you might say, okay, why just not to static cast it? And why just not to static cast the float? What will it do? You can, but basically it will truncate the mantissa. So you will get 256, and it's not the same representation that you actually wanted. Static cast is safe. You need to understand what it will do. If you told it to be an integer, it will be an integer. No mantissa for you. To actually do what we need to do here is to first translate it to uint32. If we will translate it to uint32, that means that we are actually taking the bytes that are representing the float, translating them to the same size object, and only then we can static cast it to uint64. We can static cast uint32 to uint64 because they are the same. And the only thing that the static cast will do here is zero extend. That's it. Zero extension is fine because the representation of the bytes will stay the same. You will just have a larger number of bytes there. And this is how it's supposed to work. This is not how it's working. It's much, much more complex inside the library. But this is already a step towards the good things. So if we will look here, we got this value that we wanted to get. It's exactly the same value that we've seen before, as if we cast it to uint32. With the library, it's even better. As you can see, all you need to do as a user, it's say bitcast, uint64, f, that's it. F is a float, uint64 is just a number, you don't have to play with pointers, everything is done behind the scenes. So you don't have to worry about it. As a user, you just know that this library, that's what it does. It just casts things from things to other things safely. And you get the value that you want. Let's get behind the curtains. So this is basically a header library that does most of the things during compile time. And to do most of the things during compile time, you need a lot of concepts, and concepts are great. So one of the concepts that I'm using here is a very important one that says larger size. All I want to do here is to understand if T1, size of T1, is larger than size of T2. And that helps me decide what I need to do with the types that I'm getting and what kind of casting I need to do inside. Another concept that I have to have is integral, not bool. So we are saying, are you integral type? And please don't be bool, because if you are bool, we will need to do many, many other things. Bools are evil. And this is a function that actually receives a non-integral type that we want to translate to, and a floating point type that we want to read from. And it's just a function that uses the from and translates to 2. It requires that from will be larger than 2. That means that the floating point is larger than the integer we want to use, and that means we will need to trunc it. But here we are actually doing it in a very safe way, because I'm asking if you're a float, then that means that I need to turn it to 32 bits with a bitcast. Then I need to create an unsigned type for the type you want, because I don't want to sign extend you, I just want to zero extend you. And I'm casting you from uint32 to an integer that we really want to use, unsigned integer. And then we are bitcasting that unsigned integer into an actual type that you wanted. Maybe it is something that is unsigned, but it just will not do anything in this case if it's an actual unsigned. If it's 64-bit, the only difference that you have to do is it's bitcast it to 64, because you have 64 bits, and that's it. Another function is for not integral bools and not integral bools, and it's a really easy function, because if they're both not integral, and if they're both integral and they are both bools, all we need to do is zero extend or truncate, and it's really easy to do. It's just one line that does it all. So we are making unsigned types and casting to them, and making unsigned types again, static casting, and in the end we are doing a bitcast that makes everything safe, and you will get the types that you want. Let's talk about how the library does byte arrays. It doesn't do it like that because, again, it's just a simplified version. So you can do it as a user if you really want to. If you want to cast some type into a byte array, it's really easy to do it with bitcast. So you can say that you're bitcasting something to an array, std array of bytes with the size of the something. And then you're just casting it. And if you will look at it, it's actually printing the correct thing. So it's really easy to cast now to bytes array, and in a very, very safe way. And now let's look at the from network that we've seen before. From network with my library would look very, very easy. It's just bitcast, float, because I want to turn it to float. 0 means that I want to start reading from offset 0 in the buffer. Basically, in this library, you can read the buffer of bytes in any order that you want. We're saying that we want to use std bytes, and we want to read 4 bytes out of the buffer. And these 4 bytes need to be turned to float. And that's it, one-liner to do everything. And you get what you need. So for this example, let's say that from the network, we will get 63.56. 63.56 in floating point, it's 42, 7E, 3D, 71. Let's prepare it. We're just preparing a byte array here, a very simple byte array. And we are printing it with our function from network. And we get 63.56. So it does exactly what it's supposed to do. And it's really easy for the user, hopefully. And this is actually almost the end. And I want to summarize everything up here. And the most important thing is use libraries. If you don't have libraries, understand the tools that you have. Use bitcasting. If you have C++20, use it. It's a really, really good tool that will give you a lot of power. Always use aligned memory. Never use misaligned memory, because it creates many, many different problems. Always know when you're breaking aliasing, because if you break aliasing, you may create horrible bugs. Always use sanitizers. I will say it as many times as I need to. Sanitizers are your friends. They will do just good things for you. Code should be warning-free. I don't understand code bases that keep warnings on without any reason. And most new companies that I come to, they're telling me, we had that warning for years, that's fine. Why? Why would you have a warning for years? Why would you have 5,000 warnings for years? There are companies like that. They don't care. They're saying everything works. We will not fix those things. But when they have bugs in production, it becomes clearer. Don't cast to unrelated types. Just don't do it. If it doesn't work, it's not supposed to work. And don't trust it to just work. It doesn't work. It may look cute, but then it will turn to a monster that will bite you. And you don't want to be beaten by undefined behavior. There are so many good talks about undefined behavior and what kinds of undefined behavior and what they can do to your code base. Just don't do that. And with that, I will ask if you have any questions.
Thank you, Alex. A few slides back, when you get an array of bytes, and yes, this one, how do you check for the size of the array? Or you just count on, oh, we have the right size?
There are a couple of things that I do. Sometimes I just let the user tell me the correct size. When it's just bytes like that, there's not a lot that I can do. So I just trust the user here. I am thinking about new things that I can do to make it better, even safer in this case, and not give all this power to the user. So basically, this is one of my first versions, and I left a couple of things here. For example, stud byte is not something that the user should provide in any case. It's something that I should hide, and I will. But when you're working with C arrays, it's always a problem.
First question.
Doesn't work. It does?
1, 2. Right.
This works.
Okay, so 2 questions. First one, in C++23, which legitimate use cases do we still have for using Reinterpret cast?
None.
Okay,
You don't need it.
Never?
In my opinion, no, you don't need it. There is none. The only way that you might need it is just for runtime pointers. If you need to reinterpret something, but even there, I would say use dynamic cast if you can, or use static cast. For example, if you really insist using void pointers, static cast them to the types that you want. There are really many different solutions not to use reinterpret cast, and reinterpret cast is there just because it's part of the language and it will not go away because it's written in many, many, many code bases and it will stay there forever. But if you can avoid it, avoid it. I really don't see a lot of reasons to use reinterpret cast when you're using C++23. You can always do something else, in my opinion.
And then back to your utility. First of all, you could show the barcode again. You showed it very shortly. Okay, so we can scan it. And then if you're familiar with GSL narrow, is there any comparison between that and your utility?
I'm not sure. I'm sure I'm familiar with it. I know that I needed to create this one because I didn't have all the functionality that we really actually needed. We actually use a lot of buffers that are a compile time, and those buffers just bytes, and I need to create something from these bytes. And people always forgot something, a launcher here, or used something from a buffer that was not, lifetime wasn't started yet. And most of the time it works. But when it doesn't work really, really hard.
Thank you, Alex. So if you answer to Andrei's question that we do not have any reason to use Reinterpret cast, but in your library you do use Reinterpret cast or no?
No.
Okay.
I use it in one function, and I say it's unsafe and don't use it. But you need, there's still, as I said, sometimes in runtime, someone wants to do something to transfer bytes to. I just gave it, but it's with a static warning that's with a pragma that says don't use it.
Thanks, Alex. Great talk. I really like Bitcast, and I see a future with even a safe cast, like you're a safe cast. Do you think it's something that we could propose to an official C++ 32?
First of all, why not official? I really wanted to do that. I forgot to mention, I'm part of the committee. So my only problem is that I don't have time for the committee. And this is a big problem because I really like being part of the committee. And I have 3 papers that are just waiting for the collecting dust. The concepts that we talked about, or is it Barden? He's not here. But I talked about concepts that I'm creating, new concepts to the library. It's just sitting there. It's almost ready. I don't have time for it. This is the same thing. And I plan to make a paper about standard logging in C++. So.
Thanks for the. Hello?
Yep.
Yeah, thanks for the talk. You mentioned in C++20 you can use memmove to start the lifetime of an object, and then it's even easier in C++23. What about older versions of C++? Is there a safe way to start an object's lifetime?
Memcopy. Creating an object, like I showed, creating an object and memcopying to it. Because when you create an object, you're starting its lifetime. Copying into it, it's fine. Copying from it, it's fine again. So this is the only way. Now, as I mentioned, you might get a penalty for that. Most of the time, compilers can clean it up, and you will not. But sometimes, you will get a penalty.
And you showed in your example that you worked with the data before copying it back. Is that necessary?
No. You can, again, to help the compiler, as much as you can, you should do it in one function. Because when it sees it in one function, it can optimize it out better. If you start translating it and pushing it in different translation units, you might get the penalty. So if you can do this in one function and then give it to another function that does the same thing and does the same thing and does the same thing, that's fine. You will not get a penalty in any case because the compiler will just see it and say, I know what he's doing. He just wants to use the memory directly and I will clean everything up.
Okay, thank you.
Yes, that's it.